Hi, my name is Alexandre and I'm the mechanical team lead for SONIA UV for the past 2 years. I'm also in my 3rd year of my bachelor in system engineering. Today, I'm at the École of Technologie Supérieure in Montreal to talk about the old design of our latest prototype, Dina. In this DIY video, we will show you some tips and hacks to help you build your watertight hull with all the tools that you can easily find at home. To start right away, simply activate the hydraulic pump of your industrial CNC machine.
Oh, hi there. My name is Alexandre and I'm the treasurer for the past 2 years for SONIA AUB. I'm also at my 3rd year in my bachelor in mechanical engineering. But anyways, for the first 3 tips of this video, get yourself a 9/9 spot drill. This will be the most useful tools in your inventory.
Briefly, Dina is the 8th submarine designed by Team SONIA over the last 20 years. It features a single compartment hull with a slightly modified cross shape compared to our previous prototype. The watertight hull is composed with 7 parts, which are the front extrusion, the hydrophone interconnect, the core, the connector cap, the ISC interconnect, the power extrusion, and the DVL flange. All parts are sealed with O-rings to ensure seal down to at least 10 meters. In addition, Dina's parts are CNC machined, and most of them by members of the team. The composition of the hull is mainly made of aluminum, and it also has 4 custom acrylic caps, including one with the integrated dome. Although, we didn't manage to get a great view on the first try. To prevent corrosion, all the aluminum part has been treated with hard anodizing. We also use A4 stainless steel hardware to help provide galvanic corrosion. On top of that, we add acetal washer and sheet to separate the different metals. We also paid some part for aesthetics. Besides, the box dimension of our new prototype is 76 centimeters long by 38 centimeters large by 30 centimeters height. It has a dry weight of 32 kilograms and a volume of 27 liters. You may remark that our prototype do not float by default, but we will come back to that point later. The RoboSub competition tasks are not focused on physical strength, and the transdeck environment is quite calm, meaning that there will not be much mechanical stress on the hull. As long as the submarine can withstand a pressure of 5 meters without leak, resist its own weight and thrust, it should not have any problem. With that in mind, the design should first consider geometry and feature rather than the strength. This is why the following design consideration and competition strategy are more focused on the ease of work for the whole team. Since we're making a prototype, it's normal to always be working on the submarine. It is therefore important that the interior is easy to access and pleasant to work in. Likewise, the more accessible the AUV, the shorter the assembly time. During competition, reactivity time is key to avoid the risk of missing a testing slot if an unforeseen event happens. And it's important to be prepared for these eventualities because, well, they will happen. To achieve our goal, the outer shell of our new prototype contains 4 quick-release airlocks for quick access at each end of the vehicle. This allows us to directly access the problematic component by minimizing the component to be removed. This reduces the operation time as well as the possible error during reassembly. For longer maintenance, the top airlock can be removed to increase visibility while working on the submarine. Moreover, the cross shape allows several people to work at the same time. On the undershell, the components are grouped by their function. This creates a certain electrical flow to reduce debugging time. Also, our AUV is equipped with a 3D printed clip rack system. This way, all the elements are easily secured in place. It gives the possibility to take all the components without any tool required. The only element we did not use clip are the DVL and the IMU because we need them to hang tight on the submarine frame. Without these 2 components, assembling and connecting all the electronics takes less than 15 minutes, compared to our previous prototype, which could take up to 2 hours to assemble. For our next consideration, at some point in the development of a submarine, we'll eventually realize that modeling the state equation of an underwater vehicle is an arduous task. On top of that, here at SONIA, we find even more difficult to determine the mechanical constant of the model because we do not have all the necessary knowledge. So we took our Achilles heel into consideration when designing a hull, which will allow us to simplify the equation as well as reducing the number of physical constants to be determined. This will allow the software team to develop a model-based controller instead of a more traditional approach like our PID controller we used before. According to Fawson, if we can assume that our AUV has 3 planes of symmetry and operate at low speed, we can neglect the coupling term of the hydrodynamic effect. That's one of the other reasons we have a cross-shaped submarine, because it has a symmetrical shape and it allows us to keep the center of mass very close to the geometric centers. If you're into modeling and control of marine vehicles, if you've never heard of Fawson, we recommend that you look at his work. Another reason for reducing the mass and inertia of the AUV is to reduce the thrust required for acceleration as well as for deceleration, which increases maneuverability. To achieve this, we have placed as many components as possible, including the heaviest one, into the core of the vehicle. This includes the battery, the DVL, IMU, onboard computer, and 2 custom boards. In addition, the smaller the AUV, the less mass is away from the center of gravity, reducing the inertia. Due to the pandemic, we did not have access to our workspace until mid-March. In addition, it is not possible for us to take the prototype out of the school, which limiting us to carry out tests in the Homer basin, a basin from another student club that designed a human-powered submarine. But we would like to thank the school for taking the step that allowed us to return work on our submarine. Even if the basin is small and we're limited in our testing, we were still able to test the buoyancy and sway. However, we made a big design mistake by designing a submarine that is so small that it prevented it from floating. Oops. After a bit of thinking, we found it more interesting to design a sinking prototype and increase its volume afterward than design a floating prototype and add mass to sink it. If we have in mind that 1 kilogram moves 1 liter of water, if our submarine floats too much, by example 4 liters, we must therefore add 4 kilograms of dead mass. Now, if we take the problem backwards, if our submarine sinks too much of 4 kilograms, we need to add a little more of 4 liters considering the mass of the added volume. If we use foam as material, we only add about 250 grams on the vehicle. This is more advantageous considering the mass penalty imposed by RoboSub. That being said, our new prototype will have a weight bonus of 26 points. For comparison, our previous submarine had a mass of 48.7 kilograms, resulting in a penalty of 162 points, which will give us a gain about 188 points. Because the Homer basin is about 1 meter deep, it was not possible for us to fully check the tightness of our submarine. To overcome this problem, we depressurized our submarine to a negative pressure of 80 kilopascal, the equivalent of a depth of 8 meters. After 3 days under a vacuum pressure, the gauge needle did not move a bit, confirmed that our hull do not leak. Given the fact that our DVL do not work in Homer basin because it's not deep enough and that the bottom surface is too sleek, it was not possible for us to perform experimental system identification on most of the mechanical constant because we cannot have a proper feedback. So we have decided to use a more theoretical approach to define mode of the constant needed. For the rigid body constant, we weighed all the components and we entered a result in the properties of the respective CAD and SolidWorks. Then we used the mass property feature to determine the mass, center of mass, the volume, and the inertia tensor. To make sure our data makes sense, we weighed all the assembled sub to make sure it matched the mass calculated by SolidWorks. And we were less than 500 grams away. This is mainly caused by the fact that the cables are not modeled. Therefore, we were able to check if we have respected the consideration and strategy we have defined previously. If we start with the volume, compared to our previous submarine, did not have the volume with 27 liters compared to 55. Next, if we look at the inertia tensor and more precisely on the main inertia moment and compare it to our previous prototype, data have shown that we have succeeded to reduce the inertia about roughly 72% around surge axis, 15% around the sway axis, and 47% around the heave axis. For the hydrodynamic constant, we have planned to use experimental system identification technique like the gray box identification. Since we can't acquire the experimental feedback for the moment, we use strip theory to estimate the added mass of the vehicle, and we estimate the drag constant based on our previous summary. We can't wait to go back in the water and to see you again in San Diego for 2022.